The double cage rotor, or Boucherot, I don't know, has a similar effect as the wound rotor in that it has a double row of rotor bars forming two separate cage windings. The double cage motors can be started in the same way as the normal squirrel cage induction motor. The outer cage has the greater resistance, and the inner cage, being embedded more deeply in the iron, has the greater reactance. During starting, the higher reactance of the inner cage causes most of the current flow in the outer cage, or causes most of the current to flow in the outer cage, which, having a fairly high resistance, produces a high torque with reduced starting current. So it's the same as having resistance in the windings that we saw earlier. When the motor is up to normal running speed, the rotor frequency is very low and the cage reactances are negligible. Therefore, the inner cage, having a lower resistance than the outer cage, carries most of the current. So the rotor frequency very low and the cage reactances are negligible. Just a quick point on that. Remember, we know that our inductive reactance is, what's the formula for inductive reactance? It equals 2 pi FL. Is that right? 2 pi FL, 2 times pi times F, frequency times L. So which would be the inductance. So if the F goes down, then our reactance will go down as well. And that's going to give us that effect there. Now, what's causing that rotor frequency to go down? Not sure. It just says there when the motor's running at normal running speed, the rotor frequency goes down. So that's the frequency of the current that's induced in that motor. It's not the supply frequency. So that's why the frequency can change. Or in this case, it will be very low. Typical starting values for a double cage rotor motor are 1.8 to 2 times the full load torque and 5 to 5.5 times the full load current. The disadvantages of the double cage rotor are reduced pull-out torque, lower power factor on full load. The following graph compares a double cage rotor's speed and torque curve with that of a normal squirrel cage motor. The reduction in pull-out torque can be used to advantage, for example, in the textile industry. If a normal squirrel cage motor is used for starting a spinning frame, the peak torque obtained during acceleration can break the thread because of snatch. That's I've talked about that earlier, right? That's that mechanical load that goes on because we try and spin that motor up to speed immediately. Double cage motor usually overcomes this difficulty. The double cage motor is also used as a drive for conveyor belts that may be stopped fully loaded. The motor supplies the necessary high starting torque to get the belt underway again. And there we go, there's our double cage rotor. So it's got slightly higher starting torque, but then the pull-out torque drops away more quickly. Whereas our single cage has that lower starting torque and a bit higher torque, a higher maximum torque. Do not use motors with double cages to accelerate heavy machinery. The limiting factor is the heat capacity of the outer cage, which has the greatest resistance. Because the outer cage is resistance, not reactance. That means that the heat dissipation is going to, for the greater the current is in the rotor, the more heat we're going to be dissipating. In other applications, the double cage motor will not be so effective in accelerating to full load speed. Consider the example of a double cage motor starting a fan. The shape of the fan, or the shape of the fan speed torque curve is such that with normal squirrel cage motor, an almost constant accelerating torque is maintained to almost full speed. With the double cage motor, the acceleration is initially high, but it falls off greatly as the speed increases. The starting and run-up period is longer, and the running speed is lower than with a normal single cage machine. Double cage motors can be started in the same way as normal squirrel cage induction motor. Yeah, because remember, I think we talked about this when we talked about single phase motors, is that the fan speed changes the load, right? So because the load on a fan is the air that it's moving. So the slower the fan speed, the lower the load. As the fan gets up to speed, the load will be greater and therefore will require more torque. So if this is the load of the fan, or the required torque of the fan as the speed increases, then you can see that as the speed goes up, the load goes up. So where those two curves meet, where the fan curve meets the rotor curve, the motor torque curve, that's where we'll stop. Yeah, that's where we're going to stop, because at this point here we have much more torque being generated than is required, so we get high acceleration. And as the speed ramps up, then torque required ramps up. Torque produced by the motor will come down until we get to this point here, and the motor will stop at that speed, which would be here. The single cage motor will still have plenty more torque than we need at the start, but it's not as much as with the double cage, so the acceleration will be slower. But as we reach nearer to full speed, well, the single cage rotor will produce a bit more torque, so we can actually get a little bit more speed out of that one at full load. So we're going to get faster fan speed from the single cage than we would from the double cage, even though it will accelerate more slowly because it has more speed at full load torque, or more speed at a higher, more torque produced at a higher speed. That's the one. Factors that affect motor performance. As a person likely to carry out the installation of servicing of an induction motor, you need to be aware of the conditions that can affect its performance. You will need to be able to describe how the power factor and efficiency of the motor vary according to the amount of load on the motor. Discuss the effects of reduced terminal voltage on motor performance. Describe the effects of losing a phase in the supply to the motor. Diagnose and rectify phase winding reversal in the 6-terminal motor. And discuss the effects of multiple starts and voltage surges. So let's go and have a look at some of those then. Efficiency. The mechanical output of the mechanical output power from a motor shaft is always less than the electrical input power to the motor. That makes sense, right? If we were getting more output than input, then that's free power, right? And then we just hook that output to a generator and we generate more power than we're required to go in, and then we can use the extra power. Free power. Free power doesn't exist. So we're always going to get out a little bit less than we put in, and that's because of the losses in the motor due to heat loss by the resistance of the winding. So that's our copper loss. We've talked about that before, right? Copper loss in the transformer. Same thing here. Just the fact of current running through copper is going to produce some heat. It may not be much, but it will be some, and that's some lost energy. So our motor, and that just because of copper losses, it can't be 100% efficient. Magnetizing the pole pieces and eddy current losses in the steel lamination. So again, we have those big magnetic fields, and those magnetic fields are inducing currents. So we're going to have some eddy currents moving around in our rotor and our stator. One of the things we do to prevent that, right, is we laminate those. So we don't have a solid iron core in either our rotor or our stator. We split it, and we laminate each of those thin slices of our core to stop that eddy currents coming through, but we'll still have some. Friction due to air movement, so windage, so just friction due to air movement of the rotor moving in air, but also remember we're going to probably have a fan attached to our motor shaft, so we're going to lose some of our motor power from that. And bearing friction, so obviously our rotor sits inside two bearings. It's connected to two bearings which are connected to the stationary outer casing, and there's going to be some friction in those bearings. Now obviously, granted, a bearing again is designed to be as frictionless as possible, and if you've ever picked one up and played with one, you can spin it around your finger and you can get those things moving pretty quickly, and they spin for a long time by themselves as long as they're well manufactured and got plenty of grease and all that sort of stuff. But there has to be some friction there, so that's going to be a loss as well. Therefore, our motor cannot be 100% efficient, and we work out our efficiency by going output over 100, output times 100 divided by input. That's the formula there, and that will give us the percentage of efficiency. The efficiency of a three-phase induction motor is relatively high at normal full load level and low slip, but low at low speeds where slip is high. Tests show that the full load efficiency of a 3 kilowatt motor is about 78%. As motor sizes increase, so does the efficiency. For example, a 30 kilowatt motor has a typical full load efficiency of 89%. For a 150 kilowatt motor, an efficiency of 92% is normal. So there we go. As we increase the size of the motor, we're going to get better efficiencies. I don't know if I've ever seen a 150 kilowatt motor. That is big. Don't even know what they'd use that for. It's a big motor. Variation of power factor between no load and full load. The highly inductive nature of the motor produces a lagging power factor. The graph shows how the power factor of an induction motor varies between no load and full load. Remember, we know this, right? Induction, every time we create a magnetic field, that inductive power or inductive reactance causes a lagging power factor. And we can see that there. So the horizontal of this graph here is our load, so quarter load, half load, 3/4 load, full load, and then this is our power factor here. Remember, we want our power factor to be as close to 1 as possible. That's unity. Any power factor below that means that we are paying for power that we don't get to use. So we can see here that at starter, very low loads, then our power factor is atrocious. That's like 10.1 or something like that. So it's almost completely lagging. It'd be like almost 90 degrees lagging. As our loading increases, then our power factor is going to improve until up here at our full load, we're going to have about 90% or 0.9 power factor. Remember, our power factor represents is another way of representing the angle of lag. So if our flat line on our graph, remember, is our resistive power, then the angle of lag, so 90 degrees or a power factor of low, like 0.1 or something, would be there. And then as we increase our power factor, then our angle of lag comes closer and closer to that horizontal, which would be 1. Poor power factor at light load should be taken into consideration when matching loads to rated output of a motor. Continuous running of motors at light loads should be avoided. The effects of increasing the load beyond full load decreases both the efficiency and the power factor. The current increases, producing excessive heat, and the motor speed decreases, reducing the cooling fan effectiveness. Under these conditions, the motor will overheat and could burn out. So we don't want our motor, we want to rate our motor to be at about the output level that we want. If we overrate the motor, then we're going to have it really, it's going to be really lightly loaded. We'll have a bad power factor, which is going to be inefficient. It means we're paying for a lot of power that we don't use. And conversely, if we obviously underrate our motor, then it's going to be overloaded and burn out more easily. Reduced voltage supply. The actual torque produced by a motor is determined by the motor load. It's the amount of load torque on the motor. And the available torque at a given speed is proportional to the square at the motor terminals, i.e. T what is that? Hang on. Actual torque produced by a motor is determined by the motor load. The available torque at a given speed is proportional to the square of the voltage at the motor terminals. Okay. Therefore, a small drop in supply voltage causes a large drop in motor torque, which is restored by a large increase in slip and motor current. This increase in current can lead to motor burnout. So if we're driving the motor, if we're asking it to produce more torque than it can, then the current will increase to compensate for that. So there it is there. If we reduce the voltage, then our torque will reduce. Therefore, our current is going to increase to try and keep up with the torque asked of it by the load. So if we reduce our voltage, we're going to increase our current greatly. So we don't want to run our motors with a reduced voltage supply. Starting torque reduction. Reduced voltage causes reduced starting torque. Where the starting load is not heavy, performance may not be affected, but on drives with high inertia, even though motor and starter may have been carefully selected to suit the load, there will be a longer run-up time. For example, if the rated voltage of the motor is 400 volts and the voltage applied to the motor is 380 volts, it's a 5% drop, then the percentage of starting torque equals the percent starting torque equals applied volts divided by rated volts squared times 100. So 380 divided by 400 squared times 100 equals 90%. So we've lost 10% of our starting torque for a 5% drop in the supply voltage. Yeah. So again, don't drop the voltage. Effect on speed at reduced voltage. Under low voltage conditions, speed is lower than normal and the slip is greater. The stator rotating flux therefore cuts the rotor conductors at a greater frequency. This causes the rotor current and hence the stator current to increase. The current drawn from the power supply by the motor would then be greater than the normal load current. This can cause excessive overheating if the motor if running at or near full load. The graph shows the full voltage characteristic torque speed curve for an induction motor. It also shows the characteristic curve at a reduced voltage. Note how the speed has reduced even though the full load torque in this case has remained constant. There we have it there. This is our reduced voltage torque curve, and that is our normal voltage torque curve. At every point along there, obviously, we've reduced it. We have reduced torque. Heating. Temperature rise varies inversely to the voltage, so that low voltage causes increased heating. Fortunately, the temperature increase within the likely limit of voltage variation is not dangerous except during constant running duties, where the cumulative effect from prolonged low voltage might be harmful. Normally, protective equipment wired into the motor starter circuit should prevent a burnout. The following table shows typical variations from a 400 volt supply. Have a look at that for a second. The third digit for your quiz is a 3. The third digit is a 3. Okay, so here we have it at 95%, so 380 volts. Our starting torque, we have a 10% loss. We have an 11.5% increase in slip. That's the difference between theoretical speed and actual speed. 1.2% loss in full load speed. So current will be 5% higher, starting current 5% lower, temperature rise will be 2 to 3 degrees higher. At 90% of the voltage, so we're down to 360 volts, now we got nearly 20% loss of starting torque, 23% increase in slip, losing 1.5% of our speed, 11% higher current, that's quite a lot, and our starting current is 10 to 12% lower, and 67 degrees higher. So we can see there that as we drop our voltage on that motor, it has cumulative negative effects on the operation of our motor. Avoiding reduced voltage. From the previous reasons, any part of an installation that may cause the voltage at the motor terminals to be less than its rated operating voltage must be kept within strict limitations. If you are the installing electrician, it's your responsibility to ensure the voltage drop between the point of supply, so the switchboard, and any point of the electrical installation must not exceed 5% of the nominal voltage at the point of supply, as required by ASNZ 3000 clause 3.6.2. You can keep within limits by using cable drop, volt drop calculations, and make sure the cables you are running to the motor are big enough to prevent excessive volt drop occurring, particularly when large starting currents are drawn. Oh, there it is in black and white, team. That requires no further explanation from me. It's our responsibility as electricians to ensure that we're not dropping too much voltage from one end of the circuit to the other, and we do that by accurately sizing our cables. In the following example, a maximum installation volt drop of about 5% is divided equally between the consumer mains, 2.5%, and the final 400 volt 3-phase motor supply cable circuit, 2.5%. Therefore, 400 times 2.5 is 10%, so 10 volts, so we can have a 10 volt drop at each of those parts. This results in a minimum terminal voltage at the motor of 390 volts. This is significant when you remember that torque is proportional to the square of the voltage. Therefore, for the maximum allowable drop of 10 volts in the supply voltage, the available torque at the motor shaft will be 390 divided by 400 squared times 195% of the original value. Open phase effects. If a three-phase motor is run up to speed and a break occurs in one phase, such as a bad connection or a blown fuse, the motor will continue to run as a single-phase machine at line voltage, not as a two-phase one. When running as a single-phase motor, it will gradually burn out unless adequate protection is provided. We'll run as a single phase because we now have an alternating magnetic field rather than a true rotating one, which we had with the three phases. The heating effect on the windings, so if it was start, it will fail to restart. So it will continue running while it's running, and then when you stop it, it won't start again because there's no, now we've got that single phase effect, right, alternating voltage, and we don't have a starter on our three-phase motor, so it won't start. The heating effect on the windings as a result of losing a phase depends on the configuration of the connected windings. In star, the remaining two windings carry an increased current, which will lead to the two windings burning out if circuit protection doesn't operate, because they're going to massively increase the current, and higher current in our cables means that greater chance of them burning out. In delta, the current divides unequally between the windings, with the lower impedance path of the single winding being subjected to rapid overheating. So one winding will get burnt out. Effect of incorrect winding polarity. If the motor is connected to the supply with one of its windings reversed, a large disruption in the continuity of the rotating magnetic field around the stator occurs, thus effectively reducing its output power. Either it will fail to create enough torque to start rotation, or it will make a steady humming noise when running. Yeah, it's pretty straightforward. It just means that if I've got my three windings and I've got my starts together for a star, and then my ends of the windings are connected to my supply, and I accidentally reverse the winding, then it's going to cause a weird distortion in the magnetic field. It's going to do strange things. So I need to make sure I get the connections the right way around. This is not the same as reversing the phases coming in. They will just change the direction of rotation, right? This is actually changing the start and end of the winding itself. Voltage surges are undesirable for motors in general. They occur in fractions of a second and are sometimes called voltage transients. Some of the causes are network switching, starting and stopping of motors, phase to phase and phase to earth faults, power system failures and subsequent restorations, lightning strikes in prone geographical regions. So these are things that could cause voltage surges. We don't want them. Voltage surges can be above twice the standard peak voltage of the electrical system. They will cause degradation of winding insulation and eventual breakdown. Multiple starts cause overheating, resulting in eventual insulation breakdown, leading to windings shorting out. Therefore, multiple stop-starts and other sources of voltage surge will shorten the life of a motor. Voltage surge protection is therefore necessary for motor circuit protection. Other circuits within the same installation as motors need also be surge protected. There you go, again in black and white. I have nothing else to say about that. Selection of three-phase motors. Several factors need to be considered when selecting a motor for a given application, as stated below. The nature of the load should be established, that is, high starting torque, constant speed, and so on. You may need to determine the size of the motor using power calculations. Speed control requirements and devices may also determine the type of motor chosen. You need to know the environment in which the motor will operate, particularly if it's in a hazardous location, as the motor enclosure will need to match the environment. The mounting arrangements for the motor can vary. If it is a simple replacement, you may discover that the modern equivalent of an older motor is physically smaller and has a smaller footprint, so the mounting plate dimensions will be smaller than the original. Depending on the circumstances, it may be more cost effective to put in a larger motor just to avoid machining costs. So that's what we're talking about there, is if I have to swap out a motor for one that is physically a different size, then how will I mount that new motor? If it's smaller, then my mountings might not line up anymore, and it's going to cost me more to adapt it to the original size than to just get a bigger motor. You'll need to determine the mains cable size and if there's a three-phase supply available. Obviously, if we have a three-phase supply available, then we want to use a three-phase motor rather than a single-phase. Always going to be better. And that mains cable size means that will tell me how big my motor can be. Obviously, we want to avoid volt drop. We want to avoid reduced voltage to my motor. So I have to think about the current carrying capacity of that mains cable and how much volt drop I'm going to get when I attach my motor, and that will tell me like how big a motor I can have. The cost of the motor can vary considerably from relatively inexpensive cage rotors to complicated wound rotors and associated control equipment. Maintenance availability and reliability may be affected by the environment. You will need to consider if a regular maintenance cycle is practical for the situation. Wound rotor motors require more maintenance than cage motors, and this may have quite an influence on your decision. So we're just saying there, if we're going to use a wound rotor motor, then we really need to make sure that that's what we want, that's what we need, because it's probably going to cost more in the long run. Application and reasons for selecting the following motors. Right, for the squirrel cage, general purpose, minimum slip at rated load, and it is the cheapest. So that's our kind of default option, if you like. A double cage rotor, conveyor belts or spinning frames, because of those slightly different torque characteristics, right? Lower starting current, increased starting torque, and reduced pull-out torque. And a wound rotor, we use it for water pump motors, lower starting current and increased starting torque, which can be adjusted. So if we need that high starting torque, we might use the wound rotor. Motor connections. The two ends of each winding are labelled, usually U and U1, or V and V1, W and W1. So there will be U and U1 will be one winding, two ends of one winding. Brought out into the terminal box and the side of the motor. So usually, even though we've got our windings encased inside the stator, we're going to have the connections come out. So we often have 6 terminals in there. So we'll have access to each end of the 3 windings. There are 2 different ways that these windings can be connected. They could all be in series with each other, forming a closed loop. That's delta. So they go end of one winding to the start of the next one, end of that winding to the start of the next one, end of that winding to the start of the next one, and that forms that triangle. We've seen that before. We call that delta. Or they may be in parallel with each other, having one end. So the end of every winding is all connected together to one point, and then the start of each winding is connected to our phases coming in, and that would be star. We've talked about delta and star in relation to transformers. This is no different. This is just the connections inside the motor. Most often those connections are made internally already. So there'll be connections inside the terminal box that either connect all the ends together to make it a star, or connects the starts and the finishes to make it a delta, and you just have to connect your 3 phases. However, you can from time to time find motors that will be it's appropriate to connect them in either star or delta depending on your supply voltage and what you want the motor to do. In that case, you do have to understand the stuff and connect the motor up in the appropriate way. A 3-phase motor connected in delta has a higher mechanical output, so more torque, than a star connected 3-phase motor, and it's because the greater power output of the delta configuration that most 3-phase motors are connected in delta. Star connection. So there we have it there. Connect the motor in star. Links need to be placed in the terminal box as shown. So normally when you open the terminal box, you'll see this. As I said, 6 terminals. So you got U1, V1, W1, U2, V2, W2. So if I wanted to connect it in star, then we're going to link together all of the 2s. All of the 2s will be linked together. And all of the 1s will be independent, and this is where I will connect my 3 phases coming in. One to that one to this one to this one. Oh dear, how long have I been recording without the presentation visible? Fix it in post. Okay, to connect the motor in star, links need to be placed in the terminal box as shown, as we just did. To connect the motor in delta, links need to be placed in the terminal box as shown here. So here we have starts and ends of each of the windings connected together. So start of winding number 2 is connected to the end of winding number 1. We go through that winding. End of winding number 1 is connected to the start of winding number 3. End of winding number 3 connected to the start of winding number 2, and so on. So we have that closed loop, that's what it looks like there. Installation and commissioning. The electrical connections are made to the machine, including cabling, glands, terminations and accessories in accordance with specifications and current regulations and standards. Control and protection equipment is installed in accordance with specifications and current regulations and standards. Testing confirms that all requirements of current regulations and standards have been met and that the machine and control equipment are safe to connect. Commissioning includes tests, adjustments and confirmation of operation of control equipment in accordance with specification. For example, control equipment may include but not limited to switchgear, metering, over temperature, open circuit, short circuit, overload protection. Adjustments include but not limited to phase rotation and polarity. Commissioning confirms offload and onload operation of machine in accordance with specifications, e.g. direction of rotation, vibration, temperature rise, current draw. So these are the steps that you need to take when you are installing and commissioning a motor, a new machine. Have a read of those, memorize them if you can. Alright, that is the end. I will leave you there. We'll see you for the next topic.